Welcome to 9.5, where we will be talking about parametric equations, and I will be using notes adapted from Blitzer's Precalculus 3rd edition book. And our first topic here are plane curves and parametric equations. And I'm going to try to accelerate this video a little bit, if at all possible. We'll see. So generally speaking, what we're talking about with parametric equations are, as you're seeing here, there's an equation that is in terms of t that's being used to describe our x values, and a separate equation for our y values that is also in terms of t. So as t, which is usually describing time, progresses, both our x value and our y value are going to change. And we can take t and drag it through time, generate x and y values that correspond to that t value, and then we can plot those ordered pairs. So for example, here when time is equal to 1, the 1 was plugged into the two equations at the top of the screen, and these x and y values were generated, and then a point was plotted that corresponded to those x and y coordinates. And you'll notice that the x and y axes are still here. There's no t-axis, which is interesting. The equations that describe horizontal and vertical distance of the ball, in this case, are called parametric equations. I don't have to write that down. It's written down up here. It's going to be written down at the top of the next slide. So these are called parametric equations, and the variable t is called the parameter. And we'll see in the blue box on the next page that a plane curve is a set of ordered pairs where the x and y coordinates on that curve are generated by taking a t value and moving it through an interval, which here is being called I. We see here that the variable t is called the parameter, and the equations x equals and y equals, which are both in terms of t, are called parametric equations. And those are helping us generate the curve. In example 1, we're being asked to find the coordinate of a point on the plane curve corresponding to the given value of t. You're not going to be surprised to hear that all we have to do is take that t value and plug it into our parametric equations in order to generate the point on the curve. Let me write that up for us real quick. That is the arithmetic necessary in order to arrive at an exact final answer, which I've put in this box over here. Always pay attention to the call of the question and whether or not you're supposed to be giving an exact answer or an answer rounded to a certain number of decimal places. You can handle this question on yourself, taking the value of pi as your parameter and plugging it into the cosine and the sine function. The cosine of pi is equal to -1, and the sine of pi is equal to 0. I leave the rest of the arithmetic up to you. And then we start graphing these curves, these plane curves. And the strategy here is to pick some random t values, some thoughtful t values, some convenient t values, and plug them into the equation, generate some x and y ordered pairs, and plot some points in order to get the curve. The interesting part about these curves is that the points on the curve appear in a certain order because as your t value is moving from its least value to its greatest value, your x, y ordered pairs, your points are going to appear in a particular order. So that's why we're being asked here to use arrows to show the orientation of the curve. Let's see what we end up with. Let me calculate some xy ordered pairs for us. Now that we've generated our ordered pairs, let's plot these points, keeping track of the order in which we plot them. Let's start with -5, -2. So I plotted the points in the order in which our t-values occurred from lowest to largest, least to greatest, -2 through +3, and then you saw as I was drawing the little arrows in there indicating the order in which the points appeared, which gives a little bit of motion to our graph, which we don't normally see. Let's implement that same strategy here, starting with a t-value of 0. Then we'll go to pi/2, pi, and 3pi/2. The corresponding x-coordinates, let's fill those in real quick. All right, with these ordered pairs, let's plot them in order, starting with the one corresponding to the t-value of 0. It looks to me like this set of parametric equations, if we took the t-values a little bit further, we would end up with a circle. And that circle had sort of a starting point, and it had a direction of rotation. Again, not something that we typically see when we're graphing a circle. There is a process we can go through in order to eliminate a parameter, and we'll talk through this fairly quickly and then we'll do an example ourselves. We're being given a set of parametric equations here. We're taking this y = equation. We're solving it for t, dividing both sides by 2 brings us down to this equation. I don't love the fact that the sides of the equation have been swapped. You can imagine dividing this by 2 and the 2's canceling, leaving you with just the t, and then the y also has to be divided by 2, leaving you with the y divided by 2. Then, once we have this t value in terms of y, the t value in terms of y, we can plug it into the other equation, in this case the x = equation, and we'll take our y/2 and square it, leaving us with this equation. It's not very typical to see an equation with an x and a y in it that leads with an x equals, but the purpose of the exercise was to eliminate the parameter, and we did indeed eliminate the parameter. Just be aware that you might have to then solve that equation for y, or put it into some other format. In this problem, we're also being asked to eliminate the parameter, and instead of doing the graphing process by taking t-values and plugging them in, which we could do, and in fact, I'm just going to give you some t-values to use. If it's not specified which t-values to use, then we assume that we can use any t-values we want. However, if you look at this x = equation, I don't think we're going to be plugging in any negative t-values because we don't want to take the square root of a negative number. However, the square root of 0 is 0, so that's convenient. It's also the lowest reasonable t-value to plug into that equation. A t-value of 1 would be convenient because the square root of 1 is 1. And then, what number do you think we should plug in next? Choose something convenient. How about something that is square rootable, like a 4? Okay, you can go through and generate the rest of those points and plot them in a particular order, draw some little arrows, that's great. What I want to focus on next is the process of eliminating the parameter so that we can do that on our own. I'm going to take my x = equation. I'm going to square both sides so that I get x squared is equal to t. And then I'm going to take that t value and plug it into my y = equation, which results in an equation that says y = x squared plus 1. This is definitely going to be a parabola. It's concave up because it has a positive leading coefficient. It's going to be translated or shifted up 1 unit. So the vertex is going to be at 0, 1. But you should go through the process of plotting at least a portion of that parabola by working with this table over here and plotting these 3 points in order. Another instance of parameter elimination. Let's try this one. I really like when I can end up with a y== equation. Sometimes that's not convenient, but here it is going to work. Let's take the x= equation and solve it for t. Add 4 to both sides. Divide both sides by 2. Substitute that into our y= equation. And what do we get? Y = 4 times x minus 4 over 2 squared. When you're squaring a fraction, you can square the numerator and square the denominator. So the 4 is out front, times, we've got the numerator squared, which I'm not actually going to FOIL out just yet, and the denominator squared, and then this 4 and this 4 will cancel, and we can write our answer as y = x minus 4, quantity squared, or we could FOIL it out and combine like terms and get x squared minus 8x plus 16. Either one of those is probably an acceptable answer. Notice that in this equation, we don't have the parameter anymore. The t value is gone because we eliminated the parameter. I would like to do this problem even though we've already looked at 2 other instances of eliminating the parameter, because this one is unique. We've got some trig functions in here, and the process of eliminating this parameter is definitely different. This might look familiar. Maybe x = r cosine theta and y = r sine theta. We've seen equations like that before. So if those are coming back to haunt you here, that's good. And the strategy for eliminating the parameter here isn't going to look foreign to you. I'm going to take both sides of this equation and divide by 3. And I'm going to take both sides of my y = equation and divide by 5. And then I'm going to recall that sine squared t, or theta, plus cosine squared t is equal to 1. That's the trigonometric Pythagorean identity. We will take these 2 equations. Now, seeing that I need them to be squared, let's square both sides. And then we'll take these 2 equations, substitute into these 2 locations, and we'll get our final answer. That was supposed to be an arrow. Let's try that again. That's better. We have eliminated the parameter because inside of my pseudo rectangular box there, we've got our equation without any t values anymore. So we've eliminated the parameter, and this equation looks familiar. We've seen this fairly recently. This is the equation of an ellipse. The horizontal radius, as I like to call it, is the square root of the denominator underneath the x squared value. So horizontal radius of 3. Vertical radius is the square root of 5, which is slightly longer than 2. H comma k, the center of this ellipse, is at 0, 0. 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. With the equation written as we have it in this box down here, our ellipse appears just as an ellipse. But if we were to scroll through these t values and be plotting our ordered pairs generated by our parametric equations in the order in which they occurred because of our movement of our t values from 0 to 2 pi, this ellipse would appear in a certain order, maybe starting at the bottom, maybe starting at one of the sides. In fact, let's take the t value of 0 and plug them in just real quick to see where this thing would even start. The cosine of 0 is 1, so we've got 3 times 1 is 3. That's an x-coordinate of 3. Well, there's only one point on this ellipse that has an x-coordinate of 3, so it looks like it's starting on the right. And then a quarter of the way through the process of drawing our ellipse, we would encounter a t value of pi over 2. What's the cosine of pi over 2? Well, that's 0, so you got 3 times 0. That's an x-coordinate of 0. But we have two different points that have x-coordinates of 0. Could be this point, could be this point. So we do need to calculate the y value in order to figure out at least the direction of rotation in which we would be plotting these points. So let's take the pi over 2 and plug it into our sine function. What is the sine of pi over 2 but positive 1? So that is a y-coordinate of positive 5. So we would be plotting the point 0, positive 5, which is weird. And the reason why we're coming up with a y value of 5 is because I made a mistake. Some of you might have noticed this. My mistake is over here. When I squared both sides of this equation, I forgot to square the denominator. The 5 should have turned into a 25, which means that this 5 should be a 25. So in your notes, if you didn't see that I had made the mistake, let's all go back together and make sure that that turns into a 25, which means that this also should be a 25. I was really kind of bummed that both of these denominators weren't perfect squares. And it turns out that they should have been perfect squares. So now that that's a 25, that changes my vertical radius. So I'm going to redraw my little diagram up here. I now have a vertical radius of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Horizontal radius is still 3. And my ellipse is now taller than it is wide. This is still the first point that we were plotting because it did still have a y value of 0, so that worked out. We were fortunate there. However, the t value of pi over 2 gives us now the x-coordinate of 0 and the y-coordinate indeed of 5, which matches up with our diagram, so it looks like the points that we would be plotting would appear rotationally from 0 on up toward pi over 2, and then continue counterclockwise. Alright, so we've got motion in our graphs. And we did a little problem solving there in order to find one of our own mistakes. And by our, I mean my. It happens. Human, so it goes. Right, so finding parametric equations, as often happens when we're learning mathematical topics, we learn the process going one direction, and now we have to look at it going the other direction. In this problem, we're being given an equation and asked to find the corresponding parametric equations. There are infinitely many answers to this problem. I'm going to give you two of them. For starters, if x is equal to t and y is equal to t squared minus 3, what would happen if we took our t value of x and plugged it into this equation? This would become y equals x squared minus 3. Hey, that's what that says, y equals x squared minus 3. So how did I come up with these two equations? For starters, I chose some way to model my x values. In this case, my x values are proceeding at the same rate as my t values. You can imagine plotting the line y equals x, right? Rise over run would be, that's a slope of 1. So a t value of 5 results in an x value of 5. And then all I had to do was take and do the substitution into this equation, actually. I replaced my x value with a t, because I chose x to equal t, and that is what generated this equation. So if you want to back up and take these notes in some kind of a particular order and write in some of your own handwritten notes about the process by which we created this set of parametric equations, I would highly recommend that you do that. You got to write it down in a way that makes sense to you. Let's generate another set, another pair of parametric equations. I would ask you normally to help me choose an x value, but in this case, I don't know where you are. I can't hear you. What about the square root of t plus 1? I have no idea. What's my resulting y equals equation? Same process. I'm going to take it, this x equals equation, I'm going to plug it into the given y equals x squared minus 3 equation. There we go, that's more legible. And what do we get after doing that? We get x equals the square root of t plus 1 quantity squared minus 3. Not x equals, y equals. I was distracted for a moment there. So have we done it? Are we there yet? Well, we've got an x equals equation that's in terms of t. That looks like a parametric equation. We've got a y equals equation that's in terms of t. That looks like a parametric. I think we're done. If I were you, I would clean up this equation a little bit. So let's do that, and then we'll have our two answers. I'm going to get rid of that one also, and let's FOIL, and we'll do some combining like terms. Let me come down here. Alright, so when you're typing in your answers, this would be your x equals parametric equation. Here's the one that says y equals. The order of those terms might change, but all the information is there. What are the advantages of parametric equations? Well, here's a pair of parametric equations, and if we were to convert those into rectangular form, we would get this equation. And what is that equation? It's an ellipse. The center is at 2, 3. The horizontal radius, as I like to call it, is 3. The vertical radius, as I like to call it, is 2. And you could already draw yourself a pretty accurate graph. This graph would not have motion to it. This graph, however, would have a direction of rotation, a starting point, an ending point. So that's a couple of interesting distinctions between parametric equations and rectangular equations. What if you wanted to graph this equation on a graphing calculator? Is it possible? Sorry about that. Is it possible to type parametric equations into a graphing calculator? It depends on what graphing calculator you have, but in fact you can. In a TI, like an 84 or an 89, I don't use the Nspire, but I'm sure it's in there because that thing will basically cook and clean for you. There should be, I know that on the 84 and the 89, you can hit the mode button and scroll down and over to para or parametric instead of function mode. And then when you hit y equals on the keyboard to go in to enter the equation, it'll give you an x1, y1 pair and then an x2, y2 pair so that you can enter pairs of parametric equations. But could you enter this equation into the typical y equals mode on a graphing calculator? It would be really difficult because you would have to make that thing say y equals. Or x equals, I suppose. I don't know why it is that the author chose to solve that equation for... Oh, we didn't solve that equation for x. It would be a pain. It would be irritating to have to solve this equation and put it into y equals form. Plus, you'd have to be taking a square root, so you would have to have a plus or minus, which means now you have to enter two equations into y equals mode on the calculator. It's just annoying. And for the purposes of a little additional exploration, You could go and check out an animation of the creation of the cycloid, and the cycloid above has a set of parametric equations that looks like this, and you could choose your own A value. Those are the parametric equations. To represent those equations in rectangular form, why you would solve it for x, I have no idea, but if you wanted to take those parametric equations and solve them for y, it would be an equally unattractive equation, just like this one. So there are definitely some pros and cons to using parametric versus rectangular equations. I hope that gives you a little insight into the world of parametric equations. I thank you very much for joining me, and I look forward to seeing you for my next section, 9.6, where we talk about conic sections in polar coordinates. Thanks so much.